Up there, in space, the sun never sets. There are no nights, no clouds, no shadows stretching out to obscure its light. There is only a constant, pure flow of energy, crossing the void without obstacles, without pause. And what if we told you that there is a way to capture this eternal light, and send it down to Earth as an invisible current, capable of powering entire cities? This is not science fiction, but a concrete possibility. It is space-based solar power, and it could revolutionize the way we generate electricity. Today, sunlight is already at the center of the global energy transition. Solar panels cover rooftops, fields, and deserts, converting photons into clean electricity. But on Earth, solar radiation is interrupted by the day-night cycle, the seasons, the weather. In orbit, it is not. A satellite in a strategic position, such as geostationary orbit at 36,000 km altitude, can see the sun for over 99% of the time. Solar radiation is more intense, unfiltered by the atmosphere, and available almost 24 hours a day. And that's where the idea arises, to build solar power plants in space, and transmit that energy to Earth. The idea is bold, but not new. It was first proposed in the 1960s, at the height of the space age, when the dream of unlimited energy seemed within rockets' reach. But at the time, launch costs were prohibitive, the technology insufficient, and global interest focused elsewhere. Today, however, everything has changed. Reusable rockets lower costs. Miniaturization makes it possible to assemble modular structures in orbit. Sensors, artificial intelligence, photovoltaic and transmission technologies have made great leaps forward. Space solar power is back on the table, and this time, with real data to support it. But how does it work, exactly? The concept is simple, at least on paper. An orbital station collects sunlight through high-efficiency photovoltaic panels. The energy produced is then converted into microwaves or lasers, and directed toward a large receiving antenna on Earth, called a rectenna, which reconverts the radiation into usable electricity. The beam is designed to be safe and concentrated, and the transmission can be continuous, even during the night or in bad weather on the ground. The potential advantages are extraordinary. An uninterrupted source of energy, independent of weather or geography. A solution for remote regions, islands, or desert areas lacking infrastructure. An answer to the growing global demand for energy without carbon emissions. According to a European study, by 2050 space-based solar power could cover up to 80% of current solar and wind production, with lower storage and distribution costs. A technological and ecological leap at once. Several countries are investing seriously in research. The United Kingdom has funded the Cassiopeia project, a demonstrator satellite capable of collecting solar energy in space and transmitting it to Earth. The European Space Agency has launched the Solaris program, aiming to demonstrate the technical and economic feasibility of the concept. NASA has long studied similar solutions, and China has already announced plans to test an SBSP, space-based solar power, system in the coming years. Some private companies are also moving forward, attracted by the immense commercial potential. But there are obstacles. First and foremost, energy transmission. Converting electricity into microwaves and directing them precisely over long distances requires extremely sophisticated technology. The beam must be powerful yet safe, concentrated yet non-destructive. Experiments conducted so far on Earth have demonstrated feasibility on a small scale, but transferring megawatts of power from space is another challenge entirely. Even more ambitious is the use of lasers, which could reduce dispersion but increase risks of damage to property or people if not perfectly controlled. Then there are the costs. Putting tons of material into orbit, assembling structures as large as football fields, maintaining stability and precision of the system. All of this entails enormous expenses, even with next-generation low-cost launches. Some analyses indicate that the initial price of an operational station could exceed $10 billion. However, the cost of the electricity produced could become competitive in the long term, thanks to continuous efficiency and the absence of fuel. And finally, there is the problem of maintenance. In space, materials are exposed to intense radiation, extreme temperatures, orbital debris. A small collision can compromise the entire system. For this reason, self-assembling modules, robotic maintenance, and redundant solutions are being studied to ensure safety and durability. The goal is to create resilient, autonomous facilities, capable of operating for decades with minimal intervention. Yet despite everything, the horizon is fascinating. For the first time in history, we could build an extraterrestrial energy network, capable of powering Earth from space. A technological utopia that today appears, if not within reach, at least within sight. When we look at the night sky, we see stars, planets, and satellites. But one day, we might see something new. A fixed, silent dot, transmitting invisible light toward Earth. An orbiting power plant which instead of polluting, reflects the purity of the sun. This is the vision that scientists, engineers, and visionaries are slowly trying to turn into reality. And Europe, in particular, is betting strongly. ESA's Solaris project foresees, within the next 10 to 15 years, the first in-orbit demonstration of a complete system. If the results are positive, the next step will be the construction of a true orbital power plant a kilometer long, with solar panels distributed along a modular structure, and a powerful transmission antenna. On Earth, rectennas hundreds of meters wide will receive the microwave beam and convert it into direct current for the power grid. The entire system would function like a silent symphony. The satellite, suspended in geostationary orbit, collects constant sunlight and transforms it into energy. Converters direct it toward Earth, antennas capture and distribute it. No turbines burning gas. No carbon dioxide emissions. Only light transformed into electricity, from a sun that never sets. But how close is all this? According to economic models, by 2035 we could have the first demonstrator plants capable of transmitting real energy, even if in limited amounts. The first practical applications could involve isolated areas or emergency situations, scientific bases in polar regions, islands far from the grid, temporary military operations. In these cases, having a stable energy source from space, without fuel resupply, would be a logistical and strategic revolution. Later, by 2040 to 2050, we could witness large-scale commercial deployment. Imagine a constellation of solar satellites, each capable of transmitting hundreds of megawatts, strategically distributed to provide energy to multiple continents, balancing electrical loads in real time, regardless of weather or time of day. Energy would no longer come only from the ground, but from the sky. Yet this scenario also raises profound questions. Who will control these satellites? What implications will they have for geopolitics? Energy has always been a tool of power. If one country were to monopolize access to space energy, it could redefine global balances. It is no coincidence that, in addition to Europe and the United States, China is also investing heavily in this sector, with projects like the Chongqing program, aiming to build a test facility by the end of this decade. International regulation will therefore be crucial. The frequencies used to transmit energy will need to be coordinated to avoid interference. Satellite trajectories, beam power, safety conditions, all must be defined by global treaties and regulations. No one wants to risk a technical error or sudden deviation turning an energy beam into a danger for the population. Then there is the environmental aspect. Some critics fear that receiving stations on Earth, enormous rectennas, could take up too much space, generate intense electromagnetic fields, or disturb wildlife. Current studies show that the risk is low and beam intensities can be kept below those of a household microwave oven, but public perception matters. Accepting a new energy infrastructure will require transparency, participation, and clear communication with society. But if we can overcome these obstacles, technical, economic, political, we could open a new era. An era in which humanity feeds directly on sunlight harvested in space, without the need to dig, burn, destroy. An era in which cities shine thanks to energy arriving from thousands of kilometers above our heads. Where darkness is no longer a barrier, but only an illusion overcome by science. Space-based solar power is not a shortcut. It is a long-term gamble, an investment in our ability to build the future with our own hands, beyond the atmosphere. It requires vision, international collaboration, and a new generation of engineers and scientists ready to challenge the void. But if we win, we could power not only our homes, but also our hopes. And so, the question is no longer if we can do it, but when. When we will flip the first switch, with the light of a star carried across space. If you have come this far, it means you love curiosity as much as we do. If you enjoyed this journey, leave a like, write a comment, and subscribe to the channel. It's the best way to support what we do. Your presence truly makes a difference. Until the next exploration.